4 sections of this book, so I'm gonna cut a lot of the fat, but this is what I think is most important to know. So eventually, after a lot of science speculation in the 18th century, we eventually realized, John Dalton realized, all matter is made of atoms. And atoms are like the building block of life and matter. And elements, so what an element is an element is like a collection of similar atoms, which I'll talk about what that means. An element is a collection or classification of similar atoms. So basically, one quick thing the book talks about, which I do think is probably important to know, is this idea. So another kind of scientist, Avogadro, if you've heard of him from his number, the number of moles and stuff, which you'll learn later on. Basically, he looked at some data with gases reacting. So what he saw was when you had 2 volumes, let's say you had 2 volumes of H2, and then you had 1 volume of oxygen. So when I say volume, I mean like a unit of volume. So maybe this is 2 meters cubed, maybe this is 1 meters cubed, but you could scale the ratios. If you were to combine these gases, then you would get 2 volumes of H2O. So and then he basically did the same thing for something like hydrogen gas and chlorine gas. If you're a little bit confused why I'm writing like H2 and Cl2, it's because certain elements, their atoms are diatomic, meaning if you had like hydrogen on its own doesn't really exist. Hydrogen gas is always going to be paired with another hydrogen, and we'll learn later on it has to kind of do with periodic trends and bonding in general. So if you had hydrogen gas and chlorine gas, then you would get 2. So if you had a 1-to-1, like 1 volume, you would get 2 volumes of HCl. So looking at this, Avogadro kind of reasoned that maybe you would expect, you would expect 3 to come out of this. Maybe you'd expect like, oh, the result will have the same volume as the biggest amount, which doesn't really fall in this case. What he reasoned is atoms. Let me just make sure this is recording. He reasoned that atoms, or when you have a volume of gas with the same temperature and pressure, then equal volumes of different gases will have the same amount of molecules. So even though hydrogen is different in size, and we know it's going to be smaller than chlorine, even though the sizes are different, because atoms anyway are just so small, it's going to be roughly the same amount of molecules. And that's, I think of it like when you're filling, so if you were to fill up something like even this room that I'm in with marbles versus grapefruit, you can imagine grapefruit are bigger. It's less grapefruit are required to fill up this whole thing. But if you were to think about filling up the earth with marbles versus grapefruit, the earth is just so big, it's gonna be pretty much the same amount. Like it's not gonna be exactly the same, but it's gonna definitely be to the same order. Like it's gonna be really similar. So because of this is actually how we're able to figure out, so the reason I'm saying all of this is how we're able to figure out chemical formulas. So at the time, we knew water was hydrogen and oxygen, but how do we know it was H2O? Well, we used this sort of reasoning, right? This has twice the volume. So if you had twice the amount of if you have 2 parts H2 plus 1 part oxygen, well, we're going to get 2 parts HO, and I don't really know these numbers, right? But the volume kind of tells me that coefficient. And then I can sort of look at, well, 2 volumes of H2, that would be, you would get 4, right? I guess 2 times 2, get 4 hydrogen molecules in play, or hydrogen atoms in play. Oh, well, that would be a 2 here. Well, here I would have 2 oxygen atoms in play. So, oh, 2O. Oh, there we go. H2O. This is my balanced equation, right? Because we have O2, 2O. So this is my formula, right? You could do the same thing for HCl. So H2, right, plus Cl2. Oh, these all are this is like that 1-to-1 correspondence. And by the end of it, you get 2 times the 2 times the HCl gas. Well, if you have 2 hydrogen atoms for every, volume, 2, I guess, that's kind of the ratio you can think about it, 2 chlorine atoms. Oh, well, this gives me 2 hydrogen, this gives me 2 chlorine. Oh, hydrogen chloride follows this formula. So that was sort of that brilliant idea from Avogadro to figure out some of these formulas. But we still didn't really know what an atom was really made up of until a whole bunch of experiments. A lot of experiments were ran. The cathode ray tube, if you ever heard of that experiment, they took a battery and they connected the ends to a kind of metal tube. The metal tube, we saw a bunch of particles leaving the negative end of that tube. Oh, negatives, like charges repel. That was kind of a known thing. So we could realize that, metal clearly has some sort of negative charge that is leaving that negative end, repelling away. Oh, atoms and elements, atoms have to have some sort of negative charge. So we call that electrons, right? There is this Rutherford, I believe is his name. He shot alpha particles, which are really just two proton. It has 2 plus charge. They didn't know it was protons yet, but it was 2 plus charge. So when you throw it at an atom, they notice that some of them deflected away. Now I'm not getting too much into the specifics because I don't think you care. But when it was all done and dusted, this was the basic model of an atom that was fairly accurate. Now this is not really that accurate in this day and age. Actually, is this even hydrogen? Oh my god, helium. Helium has 2 valence electrons. No way. I think this is helium. This is really bad if it's not, but I'm pretty sure this is helium. So basically, for something like helium, there are 2 protons. Oh, there's going to be protons, which are these positively charged molecules, so we call them protons. Then there are going to be these neutral neutrons, and together they form something called the nucleus. Now I'm sure this is review for pretty much any college student in middle school, high school science. I'm sure you learned this. And kind of on the end are these orbiting electrons. When you go into physics beyond high school and beyond undergrad, you're gonna realize that, this is not really the true model of an atom. Atoms that look different than this, but for all intents and purposes, this is pretty much your atom. Now, a couple things to keep in mind. So this is helium. I essentially drew helium. So helium, most helium found in our universe has 2 protons and 2 neutrons. So there is this way I forgot the name already. This is a way we notate elements. So this 2 gives us the atomic number, which is really the number of protons. So the number of protons is the atomic number. This would just be the atomic mass in what we call AMU. So protons and neutrons pretty much weigh this, or have the same mass, weigh the same. So if you have and electrons essentially have no mass. It's really little mass compared to protons. So they definitely have mass, just negligible mass because it's really small. in mass compared to the protons and neutrons. So the atomic mass, you just count up all the neutrons and protons, right? And that gives us an atomic mass. There is something called isotopes. So what we found is really the chemical properties of an element. So helium's an element. It's determined by the electrons. So that's what I meant by similar atoms. If you give me a molecule, if you give me an atom and it has 2 electrons and 2 protons, because elements are naturally neutral, like they're just going to be neutral. That's I'm pretty sure that's the case. They're going to be neutral in all cases. So if you give me the number of protons / electrons, I guess yes. Okay, this is better. Protons. Yes. Okay. The number of protons determines the properties of the atom. So if you give me a helium, this is probably not true. There could be helium with 2 protons, but its atomic mass is 5. Well, that means there's got to be 3 neutrons, because there's 5 units of mass. 2 of them are taken by the protons. The rest are the neutrons. So this would still be considered helium, though. Like, this is still helium, but it just has 1 more neutron. Now, in reality, this would actually probably be unstable. I actually don't think like this exists in nature. Maybe it does. It's just not very common. But this is what we call an isotope. So if this were real, we would call it an isotope. It probably is real. I don't know too well, but it's what we would call an isotope. So molecules are formed. So molecules are generally formed through sort of. So there's 2 types of molecules. There's covalent and ionic. Ionic compound. Don't know if you'd really call it a molecule, but covalent molecules are when atoms are being shared. So if you look at hydrogen, so hydrogen has 1 proton and therefore usually 1 electron. Oxygen has naturally 6 electrons. When we get to bonding, what we find is oxygen likes to have 8 electrons and hydrogen likes to have 2 electrons. Well, what they can do is they can kind of have shared ownership over 2 of these electrons. So to oxygen thinks, I have 1, 2, 3, 4, 5, 6, and 7, 8. 8 electrons. Hydrogen's gonna think, I have 1, 2, 1, 2. So this is what we call a covalent molecule. This is just water. Usually I kind of draw it the other way. You would have these lone pairs. Maybe flip the image upside down. But this is a covalent bond. Ionic is something like NaCl, where sodium, so this is going to get more into bonding, so I guess I won't talk about it too much, but the idea of ionic bond is when you have sodium and chlorine, sodium gives up an electron. When you give up an electron, that's some of your negative charge that you've just given away. Now you're positive, right? Because you had equal parts positive and negative. You give away a negative, now you're positive. And someone's gonna have to take in that negative. That's chlorine. Chlorine takes in the negative. Chlorine becomes negative. We would call it sodium in this case a cation. That an ion is basically a charged atom, right? An unbalance, right? An atom with an unbalance of positive and negative. These are both ions. This one's more positive. This one's more negative. So this is what we call a cation. So a cation. Cation just means positive ion. The most common sort of middle school teacher way to remember this is cats have paws, so a cation is positive. And then Cl is the chlorine here is a negative ion. We call this an anion. So once again, the high school sort of corny teacher way to remember this is anion kind of looks and sounds like onion. Onions, I guess, are generally negative. They make you cry. So anion would be for negative ion. So this has been pretty much what you need to know from 2.3 to 2.6. All of this will come back in later chapters, but it's just an introductory point for right now. So yeah, thank you for watching.